Good morning, everyone. How you guys doing? Good. So welcome. Welcome also in our 5 overflow rooms that are also watching this session live. It's a popular session, so we'll make sure we make it worth your while. My name is Andre Dufour. I run the AWS Step Functions team, and we also have with us today Nick Whalen, who's a principal software engineer at Novartis, and he'll be presenting a use case that I hope you'll find interesting. I want to kick us off today with a statement that's hopefully not too controversial for most of us. Modern application development enables rapid innovation. Now, if you guys have been going to reInvent for a little bit, or even this time around and taking in the content, you may have noticed that modern application development, or MAD, pervades a lot of the content in the sessions this year. Now, MAD is not something that AWS came up with on our own. It's actually based on feedback that you, our customers, have given us around how you out-innovate your competitors, how you innovate better in the cloud than you could with traditional on-premise server-based technologies. And so we're going to cover that in today's session. There are a number of different pillars associated with modern application development. We're going to go into a bit of depth in 3 of them: elasticity, microservices and modularization, and interoperability. And of course, we're going to spend a good amount of time grappling with the issue of how do we manage state in a microservices-based distributed application. Now, you may have noticed on the door as you made your way in, this is a 300-level session, so it's an advanced session, and as my colleague Tim Bray likes to say, there will be code. So I'm not going to give you a Microservices 101 course here, but I thought it would be useful to have a common vocabulary, a common framework, so that we're all on the same page. One definition of microservices that I really like is that a microservice should encapsulate completely a single business function of your application. Another aspect of microservices that is important is they should be independently deployable from the rest of your application. And we'll see that this makes fault isolation and correction and ultimately innovation velocity easier. So imagine different types of business functions that could be part of your application: processing user input, acting as a data persistence layer, or even interfacing with an IoT device that forms a part of your application. Imagine now that you have a problem receiving telemetry from your IoT device. Well, in contrast to a monolithic application where potentially you could be looking for that problem throughout your entire code base, with a microservices-based architecture, if you've properly factored things, you know where to begin your search. It's going to be in the microservice associated with that IoT device. You can perform the fix, test it in isolation, and most importantly, deploy it independently from the rest of your app. This makes it much faster than if you're contemplating a sort of deploy the whole world type of scenario. Innovation makes its way to your customers much more quickly. Now, in microservices, we tend to communicate in asynchronous fashion. We're passing messages, we're using queues, we're using an event-driven architecture. We tend to not rely so much on shared data stores because these will introduce lock contention and synchronous types of dependencies which have failure modes that we would prefer not to enter into. So it's all fine and well to be nicely factored and everything's decoupled and I have microservices that don't really know a lot about each other. But how do I deal with problems when they arise? What happens if the microservice over here goes down and comes back up, comes into service in some unpredictable fashion, right? It may have its own personal perception of the world, which may differ from microservice B over here. Microservice C may react in some unexpected way to the failure that happened over here. And very quickly, if you're not careful, you can find yourself in a bit of a split brain scenario, not knowing what state your application is in. So how do we deal with state management in a distributed type of microservice scenario like this? Well, the answer is in the question. We need something that looks like a state machine. And one way that we can do this is by using a service that offers state machines as a managed offering. And of course, that's AWS Step Functions. Now again, it's an advanced session. I'm not going to give you a full primer on Step Functions. I assume that you know a thing or two about the service. If not, this is your one slide to catch up. So we'll spend a bit of time here. So with Step Functions, the way it works is you define your state machine's business logic using Amazon States language, which is basically JSON. So with this, you'll specify the structure of your state machine, which is rendered for you visually. You can see that in the central graph here in the form of a flowchart or a state machine. And there are different types of states that can be employed in the state machine. Some of them are action states, right? We may be doing something like invoking a Lambda to do work for us, or we could be interfacing with an EC2 or ECS or EKS, or even on-premises-based worker to do work. There are also choice states, which will send you down one branch or the other of the state machine based on the output of previous states. And then equally, we have states that enable processing in parallel, for example, for big data type workloads or even medium data. Now, one of the cool things about Step Functions is its traceability and debuggability features. So if you can see on the far, I guess this would be right-hand side for you, you have the opportunity to look at what path was traversed in the state machine for a given execution. The nodes that are highlighted in green is where this execution actually went. And if you were to click on any one of those nodes, and we'll see this in a subsequent slide, you can actually see the inputs that were provided to that state, any errors or exceptions that were thrown, and the outputs that were generated. So it makes it really easy to troubleshoot as you're developing your state machine and your overall application. And it also works very nicely when you're operating at scale. Also, your data is persisted for up to a year, so you have a nice auditable execution history, and all of this scales elastically for you, so you don't have to worry about provisioning or managing anything. So the way we're going to structure our discussion today is by using customer use cases. So these are folks like yourselves who have come to us and said, hey, we have a couple of patterns that we think would be of use to the serverless and modern application development and Step Functions communities, and we'd like you to highlight them. So that's what we're going to do. I'm going to talk through 3 customer use cases, and I'll do my best to surface the patterns that I think might be of interest and reusable for you. And then Nick will take the stage, and he'll talk in a bit more detail about how Novartis has used Step Functions to manage state in distributed applications, and we'll do a bit of a deeper dive on their use case. So the first one we're going to talk about today is Xylem. Xylem is a large company involved in water technology, the transportation, distribution, and efficient usage of water. And they had a big problem. Their data lake team was interested in making the data from tens of millions of endpoints available to all their stakeholders, persisting it forever. And they needed to do this with a team of only 4 people. That's 4 people for building it, 4 people for maintaining it. Now, in a little more precise terms, their specific application consumes an arbitrary number of binary files, transforms them, and loads them into the data lake in a Parquet format. And this is a pattern of interest, the very first that I'd like to call to your attention. You know, some people take a look at Step Functions and they say, okay, I get it, it's a state machine. I probably need, you know, a 100-state machine to really get the utility out of this. And they very quickly dismiss these small, useful workflows. Many customers have found some value actually in using Step Functions for 3 or 4 state machines that do a really simple data transformation operation like Xylem does, right? Many times you find yourself taking data out of Redshift, transforming it, putting it into S3, taking data out of an on-premises resource, applying a transform, loading it into Dynamo. 3 states, easy, a little bit of error handling wrapped around it, and you're off to the races. So don't dismiss small state machines as a useful pattern, and this is what Xylem has taught us. Now, another aspect of their application is they needed it to be elastic. See, they were coming from an on-premises world where their approach was anything but elastic. They had a data center, they had servers, and every now and then they had to ingest new large customers into their system. And this obviously consumed a lot of resources, and they had to provision for those peaks. But in actual fact, the average utilization of their infrastructure was quite low. So a large peak to average difference. And so the reason they needed something that was elastic is they don't always want to be paying for something that's provisioned for peak when in reality it's lightly used. And so this is the second pattern of interest that I'd like to call to your attention. When you have something that does have this large peak to average variation, it may behoove you to consider a serverless technology as part of modern application development, because with serverless, including step functions, Lambda, API gateway, et cetera, you're only paying when your code is actually running, as opposed to paying by the hour when you've provisioned something. So this is what Xylem did. And the other thing, I told you they had to do this with only 4 people to build and 4 to maintain. Well, serverless tends to attract quite a bit less operational investment in terms of people and hours than provisioning servers, because with servers, you're forever having to patch them and deal with them. Even if they're virtual machines in the cloud, you can realize some economies in terms of your operations if you move to a serverless approach. So that's what Xylem had to say about that. So let's have a look at their solution architecture. How did they actually do this? So you can see that it's a combination of step functions, batch, and Aurora serverless. And step functions and batch pair pretty nicely. We'll see it actually a couple times in this presentation. Batch, of course, provides the containerization framework, and on your behalf will provision resources necessary to execute a batch job. And the role of step functions in this is to actually launch the batch jobs, orchestrate their execution, and if any error conditions arise, it deals with retries and any sort of error handling logic. And Aurora Serverless, in this instance, acts as basically an index of files that are going to be in the data lake. So there's a single solitary EC2 instance in this. It's an edge node responsible for gathering a list of input files as Xylem is ingesting new customers. It passes these to step functions, which validates that the list is valid, it's correct. It then determines which types of transformations need to be applied to these binary files in order for them to make their way into the data lake. In some cases, there will be one. In some cases, there will be multiple. And step functions via Lambda launches batch jobs for each of these types of transforms in parallel, monitors their execution, keeps the tables in Aurora Serverless updated as to the status of those executions, and when everything is done, it notifies Aurora Serverless to indicate that these files are now available in the S3 data lake. Now, one example that Xylem gave us, just to showcase how convenient this approach is for them, is if they had to ingest 6 months worth of data for 500 new customers, which is a very realistic prospect for them, it's about 9,000 files to be processed. And if they were doing this with their on-premises installation, it would take about 20 hours of processing. Now, 20 hours is precariously close to 24 hours or a day. And if they found themselves spilling over that 24-hour boundary and into the next day, have I lost the mic here? You guys hear me? Okay, that's better. Yeah, if they found themselves spilling into the next day, they would then begin to accumulate a backlog as the next day's processing kicked into action. But with this approach, actually step functions can launch in parallel the 9,000 batch jobs associated with the transforms. It takes about an hour, 1 to 2 hours, and it costs $20, right? So contrast that with entire data center, $20 1 hour. So this is a really nice approach that you may wish to consider. The next use case that we're going to consider is Coinbase. So everyone knows Coinbase as the digital or cryptocurrency exchange. And Coinbase wanted to move even further into modern application development practices. Specifically, what they wanted to do is iterate more frequently, innovate faster, and this amounted to deploying more frequently so that the innovation that they create from their engineers could make its way to customers sooner. And they achieved some pretty impressive results. They reduced new account deployment time, they increased the reliability of their deployments, and as relates to their mission-critical services, they were able to deploy them 7% more frequently, right? So 7% faster innovation making its way through the pipeline. How did they do this? Well, they basically built a deployment system, and there are 2 components here that are probably worth diving into. The first one is CodeFlow, which is their configuration management system. So it contains information about what needs to be run, right? It defines the application. We're talking about Docker compose files, user data, that sort of thing. And in addition to that, CodeFlow contains information about the infrastructure on which to run it. What elastic load balancers are involved, what auto-scaling groups do we need to create, what are the rules associated with those, and the permissions. And the second component is something Coinbase has called Odin, And this is the Step Functions-based application that's sitting there on the diagram right next to CodeFlow. And Odin is responsible for actually orchestrating the deployment, provisioning resources, and so forth. Now, it's worth calling out at this point that there are managed AWS services that can do many of these things for you. But in Coinbase's case, they had some more specific requirements and they wanted more flexibility, and so they chose to use step functions to fill that gap. And I'd just like to say that's a perfectly acceptable pattern, right? If the managed AWS offerings aren't doing it for you, you're perfectly welcome to use a service like Step Functions to innovate around that. We want you to do this, we'll support you. Okay. So how does this work? Well, a deployment request makes its way into Odin. Odin validates that the user data is present and that the deployment request is correct, and then it begins to execute the deployment. Specifically, it provisions a new auto-scaling group, waits for that auto-scaling group's resources to come into service, executes the software deployment, waits for that to become healthy, and then deprovisions the old resources associated with the initial deployment, because we're doing immutable deployments here, right? Yeah. So you can imagine that if anything went wrong in an unpredictable way at any point during this process, it could be pretty bad, right? You could find yourself with instances behind a load balancer serving production traffic that are unhealthy or that are not known to be healthy. And so this is what Xylem not Xylem, we're talking about Coinbase at this point. What Coinbase particularly liked about this approach was that Step Functions kind of forces you to always know what state your application is in. Even if it's going into a failure mode, it's made rather explicit what state you're in, and so there's very little chance of this unpredictable type of error stuff emerging. Let's have a look at their state machine here. So at the very first stage, we validate that the deployment is correct, lock resources that we're going to be using, validate that the resources are indeed locked, and execute the deployment. Wait for the deployment to be complete, and then wait for it to become healthy, right? This is sort of the happy path. But as you can see, there's a bunch of branches in this diagram going off to the right. These are all the error handling conditions, right? Coinbase did a really good job of making sure that they're catching errors and dealing with them appropriately, attempting remediation if they can, or at a minimum, tidying up and cleaning up the failed deployment explicitly. And if everything goes wrong, they wind up in this failure dirty state that's at the very bottom there in red, where they have the opportunity to automatically page in resources, humans, that are going to help tidy this up. So the pattern of interest that I would encourage you to take away from this is explicitly failing to a known state. Because there's nothing worse when you're on a call and you're trying to figure out what's going on with your system and customers are impacted than not knowing what state you're in, right? You don't want to spend a bunch of time figuring out what state you're in before you can start working on remediation. And using something like Step Functions in this way is really helpful. So the final use case that I'll talk to before I hand you over to Nick comes to us from Granular, who is a farming technology company. And Granular's business basically is making data from agricultural equipment available to stakeholders so that they can take action on it. And Granular had legacy infrastructure. I know, shock, horror. How many of you have no legacy that you have to worry about at all? You're perfectly free to frolic in modern application development, entirely serverless, no legacy at all? Okay. Couple of you, the lucky ones. Most of you have some legacy that you need to deal with. And legacy isn't necessarily a bad thing, right? It's doing something useful for you, but it may not be an application that continues to evolve that much, or there's not a return on porting it to different types of technology stacks. And that was the case for Granular. They had a piece of software that was doing useful data transformation. They don't really want to mess with it too much, but they do want to wrap it with some more modern application development technologies, container-based applications, using Lambda where it's appropriate. And so they wanted to draw this all together. And this is the pattern of interest here, using step functions for state management in a case where you have a heterogeneous technology stack, right? They're using Python in some cases, they're using C# in others, Windows servers, Kubernetes containers, And they wanted to draw all of this into a single type of application. They did consider, of course, developing a homegrown solution to orchestrate this workflow, but quickly realized, hey, we're a farming technology company. We're not necessarily in the business of developing workflow engines if we don't have to. And with Step Functions, they were actually able to get a prototype running within a week. And I'll show you what that prototype looks like here. So you can see the color coding here indicates the different types of technologies that are present in this application. You've got Python containers running on EC2 instances. You have Lambda functions, also written in Python. And you have some code written in C# and .NET that's running on Windows servers in an auto-scaling group. So a pretty motley assembly of different things, but it actually all presents as a single application in this one state machine. So what are they doing? The very first state here is a container running on EC2, as I said, and all that one does is accepts a URL for a resource, for a file that's located in an on-premises data center. And this state brings that file into the cloud, puts it into S3. The pre-translate sniffer is a really simple Lambda function written in Python that determines whether a certain type of pre-processing is going to be required. And if indeed that pre-processing is required, we find ourselves going down the Slingshot preprocessor branch of the state machine. Now, Slingshot is a tool that applies a certain type of transformation to the data. That one happens to be a Python container again, which then hands off its output to the translation state. And this is the one that was kind of their legacy infrastructure. It's a C# application, runs on Windows servers in an auto-scaling group. But by the way, I'm not implying that Windows is necessarily legacy or that C# is legacy. It just happens to be the case in this application, just so we don't get into any controversy here. So that one does its thing and then passes its output to the transformation state, which is, again, a container written in Python. And the really cool thing is that this all just works together, right? And you have a unified way to actually troubleshoot, to debug, and to reason over this application in a single state machine. Now, before I hand you over to Nick, let me just tee up some of the issues and challenges that he and his team are facing. So they're at Novartis, and his job is to basically provide data to scientists and give them a tool to run image analysis at super high scale. And they were able to achieve some pretty impressive results, right? They reduced cluster processing times. They improved operational efficiencies. They managed to deliver a tool that delivers reliable, reproducible results to their scientists, and they were able to do this with a really small team. So it's my pleasure to introduce you to Nick Whalen.
Hi, everyone. I'm Nick Whalen. As Andre mentioned, I work for Novartis. I'll just quickly talk about who we are before I delve into how we use step functions to solve some of these challenges. So I work for Novartis Institutes for Biomedical Research. For purposes of brevity, I'm just going to call it Novartis. Essentially, we're the innovation engine of Novartis. So we focus on technologies that promise to produce therapeutic breakthroughs for our customers who are the patients that consume the drugs. Worldwide, 6 research campuses, 200 projects in the clinical pipeline, and many more clinical trials in progress. Before I jump in to the architecture and step functions in general, I want to talk a little bit about what we set out to do with this application. So we needed to empower the scientists to directly run image analysis without having to depend on cluster experts. We had cases where there were 5 or 6 different scripts that almost did the same thing, but they were very customized, not extendable. And finally, we hoped that by providing them this simplified tool, it would speed up their assay development and enable them to focus more on the science, which is what their job is, and not on technology or software. So high content screening image analysis has been around for a while, but I'll just talk about the workflow just to give you some context. So essentially, if we start from left to right, we have biological and or chemical material that's placed into wells inside plates. You could have anywhere from a couple plates to 1,000. And essentially, for an imaging assay, each well gets imaged, which produces hundreds of thousands, even millions of images across channels and wells. Within these wells, if you're talking about cellular data, we could have anywhere from 1,000 to 5,000 in each well. So the classic feature engineering approach is we detect the objects in the image, and then we extract features from them. So you could think of what is the pixel width of a nuclei or a cytoplasm. These features can be anywhere from 200 up to 5,000. So you could think of the features as the columns in the CSV and the individual cells, unique cells, as the rows. So it produces up to several terabytes of tabular result data. I'll get into this a little bit later, but we have a fancy cluster running AWS batch. Things scale up nicely, but it really doesn't matter if you can't merge these results together and provide a usable package for the science to make decisions on. And that's what we used step functions for in this case. All right, so the application itself is pretty simple. It supports two entities. So you have a run, which is basically a pointer to an array of jobs. And then you have your run details. So on the run details page, we enable the scientists a page where they can upload all the inputs and select their image input and submit the cluster analysis. And then they monitor the state of execution and download the results from the UI when it's done. So the architecture. If we go from left to right, a client makes a request over HTTPS, which hits a load balancer in a VPC. I think Andre mentioned was Xylem that has a controller app. We have something very similar, so it's essentially a Java web service sitting on a EC2 instance, and it contains the business logic to process the request from the science and send the request to AWS Batch for scaling. So in this case, AWS Batch will scale up, load the images from S3, perform image analysis, and produce hundreds, thousands, hundreds of thousands of individual small CSV files. We send messages to monitor the state of each job, each worker, in SQS, and we persist the state in Amazon Aurora. Eventually, an event will be emitted, which will be the input for our merge and post-process state machine. I'll get into this a little bit, but we're not, just to be clear, we're not sending like a list of like 100,000 S3 object keys. We're actually sending one object key that's a JSON that contains all the references to those individual paths on S3 as input for the merge and post-process state machine. And then finally, the finalized results after they're merged and or post-processed are written back to S3 and available for the scientist to download via the UI. Okay, so merging and post-processing state machine. If we talk about this from top to bottom, essentially we're using Python, Lambda, and AWS Batch here. So we're using Lambda to make requests to AWS Batch, and then we're polling for state. So the first step is to actually calculate the optimal compute requirements for each plate barcode that needs to be merged together. So you think of it as grabbing a whole bunch of individual CSV files and then determining what the optimal memory is needed in batch to do the work. It passes those list of basically memory requirements, compute requirements, to an execution block that submits the jobs to AWS Batch with the recommended compute resources. We poll over the state until all the jobs have reached an end state, and that can be either error or complete in our case. We support this notion of an Ifelse, so you'll notice the merge job array complete and post-process run. So this choice state, if true, will also submit to batch and poll, But the notable difference is instead of submitting to a container in AWS Batch that has business logic to merge, it actually has business logic to do more statistical calculations on it, as specified by the science. Finally, we make sure that all the jobs have reached an end state, and we validate that the paths to the result files are correct for download in the UI. So here's just our if-else. On the left, we have our merging only, and on the right, if the scientist so chooses, we've also do some aggregation. All right, so you're going to notice kind of a theme here with all these sort of repeats itself, but I'll call out some things here. So in this first block, calculate compute requirements, we have a result path that's going to a GUID, and this is going to pass basically an array of compute requirements to the next caller, which is submit merge job array. All the states here have a retry block, and because we're using Lambda, we're always catching the exceptions, in this case either a service exception or an SD client exception. I think it's important if you're new to step functions to understand the different layers of abstraction, because you're using Lambda in this case to do work, to request work from another service on your behalf. So there's a lot of areas where things could go wrong in that chain, both in Lambda and in Batch. The other thing I want to call out is always use exponential backoff and retry. You'll notice in the last 3 lines, there's an interval in seconds, a max attempts, and a backoff rate. That's all it took to implement exponential backoff and retry. It makes it quite simple, and I've seen it in action. Definitely useful. I definitely recommend using it. So now that we've passed the list of recommendations for optimal compute requirements, we're actually going to submit the jobs to Batch. There's nothing really different from structurally between this step and the previous one, although the next step will be a wait state because we're going to poll. So in this case, we're passing the AWS Batch job IDs that get returned from the submit job API, and we're going to call AWS Batch and ask for the state over and over again until we know that they've reached end state. Right? So the only thing I want to call out here is that as we're iterating, and I'll talk about it a little bit more later on in the presentation, there's a variable on the second line called wait time. We found out the hard way that if you have a long-running process, there are certain limits in step functions that will kill the execution in the middle. To mitigate that, we introduce this variable which essentially spaces out the time that you iterate, right? So if you know that you have a large set of files and it's going to take potentially hours, you may hit that maximum event time of 25,000 events. So you'll want to do the work up front to take out variables like that so you have a fine level of control when you execute. All right, so that's all fine and good, but that's not the only place that we use step functions in our workflow. So by show of hands, anyone that's used AWS, how many people have had to move data from their on-premise corporate data center into AWS? Somebody at least? Yeah, a couple of people, right? So we were faced with this, well, it was a challenge in the beginning because there was no good way, and we were using serverless technologies. We're not using traditional mount points on servers and things like that. So we had to figure out a way to get large amounts, and I'm talking about terabytes and even petabytes of image data into S3. So we built a simple state machine. And if we look at this from top to bottom, the first block, send plates to SQS, simply sends a message actually to an SQS queue that has a trigger. And it's basically comparing the count of files that we know to exist in our corporate data center and the count of files in S3 for, in this case, a specific plate with thousands of images in them. We iterate until essentially the count of our on-premise matches S3. And we're doing this by with a Lambda that's connected to the SQS queue, pulling the images in groups of, let's say, 50 via HTTP. So it turned out to be a pretty good pattern as long as you have a network that can handle that kind of load. So that was useful. Another one, even simpler, is we wanted to enable our scientists to subscribe to cluster run state changes. So you could think of a case where they submit something really large, and they don't want to sit there and just push refresh on their browser over and over again and watch the little bars go to 100%. These could take all day. So we have these two state machines, the one on the left, which creates a notification topic if the science decides to subscribe, which creates a custom SNS topic for that run. You could think of it as like HCS 100 topic or something. And as the array of jobs on batch are processing and we're persisting the state, we're sending notifications to this state machine. If the state machine detects a notification that we've defined as an end state, we will send a message to the topic and finally return. The other thing I want to call out is this step function, this state machine in particular, cleans up after itself because it deletes the topic that we created on the left. So that was also kind of nifty. All right, so some general points. I think when I can speak from personal experience. When I started using step functions, I thought that I could create this massive step function that did everything in my workflow in one state machine. And I'm going to say from experience, it was actually much more beneficial to decompose and have a series of smaller state machines that did discrete tasks with far fewer steps. It was a lot easier to maintain. We also have a small team that supports us. There's only 3 people, so it can become challenging if you had this monolithic thing. And it's also hard to communicate if you handed it off to somebody else that has like 1,000 states. Another thing, I recommend using S3 to persist and iterate over the large data sets. So pass the object keys instead of filling up the input to AWS Step Functions. I believe there's a limit there. Andre can maybe, yeah, he's in the affirmative. There is some limit. We avoid that by actually writing a JSON file with the references to the object keys in S3. So I definitely recommend that. And then finally, kind of said this before, but extract certain business functionality by state machines so that you can easily isolate and find out what went wrong in a specific part of the workflow. So error handling, it goes without saying that if you're building stuff, you need to understand the possible exceptions that can happen in each step. But with step functions, you need to determine if you need to stop the execution altogether or if you can recover from it. It's dependent on the use case. An example in our use case is the scientist would rather have partial results instead of no results at all. So in our case, we define that even if there's an error on one of the merging jobs, we continue processing and note that error so that it gets persisted. Always use exponential backoff and retry. It's basically free. It's 3 lines of code. I don't know why you wouldn't do it. And always catch exceptions and do something with it. And then finally, know the limits. Don't be like us and find out after you start building step functions. Use a for loop or an iterator to iterate over large data sets and avoid hitting the maximum number of 25,000 history events in an execution. I actually posted, this is a screenshot from our CLI just to prove that we hit that on long-running executions. So it's been a pleasure speaking with you. I think we'll be outside after for Q&A. I'm going to hand you back over to Andre. So thank you.
Good job. Thanks, Nick. That was really interesting. So let me ask the audience here. How many of you manage or lead a team? OK, quite a few, actually. How many of you super enjoy it when your boss goes directly to your team to give them direction and bypasses you? Anyone? OK, no one. I don't either. Thankfully, I have a great boss who almost never does this, but there's still some part of me that wants to know when he's entering my team area, potentially to give them direction. And I also want to know what sort of mood he's in. And this led me to build a step functions-based application called the boss detector. So here's the problem statement. Let's know when my boss enters the area, and I'd like to know whether he's happy, sad, hungry, tired. Which version of Jesse am I dealing with? And you can see the different shades of this gentleman. So how does this actually work? Well, it starts off with AWS Deep Lens, which, if you don't know, is Amazon's machine learning-enabled camera. It was launched at reInvent, I believe, 2 years ago. And so I loaded a software image into Deep Lens, which, when it detects movement, at some regular interval, it will upload snapshots of the scene into S3. Also present in S3 is a reference image of Jesse. You can see his face there. And that's going to be used in a subsequent step. Now, every time a new snapshot is uploaded from Deep Lens into S3, this triggers a Lambda function, which launches the state machine that you see here. And we're going to run through it. The first state is called check notification time. And this is just a way to avoid repetitious notifications. If he goes into the team area, he's probably not going to be there for just 1 second. So I don't want to get a notification every second. I insist that 30 minutes of time pass between each notification of Jesse's presence in the team area. So if a suitable amount of time has passed, then we will move on to the detect Jesse state. And in this case, we make a call into Amazon Recognition using 2 images, the scene that was uploaded from Deep Lens and the reference image of the person we're looking for. And Recognition will tell us whether or not Jesse was present in the scene. And if he actually was, we pass through the choice state and move on to the analyze Jesse state, which will analyze his facial expressions based on the snapshot and give me an array of emotions that I may be dealing with. This is then assembled and passed on into the notify team state, which makes use of Amazon SNS to send me a text message with all the information I need to deal with this situation. So here's a little bit of code. This is just a simple Python-based Lambda function that shows the detection of emotions. First couple of lines are just setting up some variables. Then I make a call into Amazon Recognition, which will return an array of faces and emotions. And I've snipped out some of the code here, but all it actually does is iterate through this array and assemble a string of emotions that are present with high confidence, right? And so this is returned ultimately in the final statement here in the variable JD emotion into the main state machine. And we can see this in action here. This is the execution history. I've truncated the top. We start at step 17 here. And this is how you can actually use this to troubleshoot and debug your state machines. So if you look at step 19, it's been expanded for you. And this is the output of the analyzed Jesse state. And you can see a variable called JD emotion has been returned to us, and it contains the string he looks happy, which is good. And then if you look a couple steps lower, what we're looking at is the task state entered execution history event for the notify team state. And you can see that the input there contains that same variable, JD emotion, and the string he looks happy. So imagine how easy it would be to troubleshoot something using an approach like this, right? You can make your way through the state machine. Was the input what I expected? Was the output what I expected? Did it get corrupted somewhere? You can easily detect where you need to look for problems. It's a nice modular approach like that. So let's have a look at this in action. This is the culprit. He has entered the team area. This is a dramatization of an upload from Deep Lens into S3. And if we click through here and look at the output of the detection step, the part in red here shows us that, yes, indeed, Jesse is present in the team area. The images match with 99.89% confidence. And here's some of the information that was returned to us when we performed the facial analysis. So we won't discuss the age range, but you can see that apparently Jesse is happy. We have about 78% confidence in that statement. There was also an indication that he might be calm, but that's low confidence, so that didn't make its way into the string that was ultimately assembled. And then finally, this all gets packaged up, hits Amazon SNS, and I get a text message. Warning, Jesse's in the team area, but he looks happy, so we're probably good. So there's a pretty high probability that Jesse is in one of the overflow rooms watching this. So I'd appreciate it if you'd give him a hand for being a good sport and submitting to this experiment. Thank you, and thank you, Jesse. Now, why have I shown you this potentially career-limiting example? Well, obviously I had a point to make. See, it's kind of a silly little application that didn't need an auditable execution history. It probably didn't need a whole ton of modularity or elasticity or any of the goodness that comes with step functions. And my first instinct, and maybe for most of you this would be the case as well, would be to just hack something together in maybe a single monolithic Lambda function, or maybe have a script running on an EC2 instance somewhere. And of course you could do that. But then I asked myself, well, what penalty do I actually pay for doing this in a quick and clean way, using step functions rather than quick and dirty? Well, not much, it turns out. I only had to write 49 lines of Amazon States language code. Most of those just contain curly braces and other JSON artifacts. I hardly edited anything except the actual structure of the state machine and a couple of the ARNs that point to the Lambda functions that I was using. So not a whole lot of extra typing. There's a nominal cost here that you pay for the use of step functions. It's basically to cover the expense of persisting the data. You couldn't really do it much cheaper yourself. And in exchange for this, I actually have an application which will now grow with me should my office surveillance needs increase. And I've got a modular architecture. It's elastic, it's secure, as befits a modern application. I also have a traceable, auditable execution history. So as my needs move from experimentation and kind of fooling around with a little application to something that scales into production, that's already there for me. I have built-in error handling, and Nick showed us that with just 3 lines of code, you can leverage the retries and catch exceptions. And I have a visual representation of the overall workflow, enabling me to troubleshoot it very easily. So I think that'll about do it for us today. It's been a privilege being here with you. From Nick and myself, thank you for joining us. Now, there are a couple of step functions folks in the back of the room there standing around, and maybe they'll give us a wave. They're gonna help us take some questions. Nick and I will also kind of hang out in the room and probably in the hallway if you'd like to approach us. If you want to get in touch, here's how. Once again, it's been a privilege being with you. If you have an opportunity to fill out an evaluation, we'd sure appreciate it. And with that, I'll wish you an awesome reInvent.